All right, let's go ahead and talk about section 5.1. Now, 5.1, what's it going to be about? Hypothesis test. The only big difference now is that we're going to include in here what we're going to call the normal distribution. Now, what you see on my screen right now are four different randomization distributions, which all of these were used using the idea of like bootstrapping. They had one original sample that was used to help in an argument about a null and an alternative. And then what it's going to say here is that there's something known as the central limit theorem. And what it says is that as long as your samples are of sufficient size, when you do a bootstrap or a randomization distribution, that the shape of it is going to look like this, where you've got the one hump in the middle, tail to the left, tail to the right, symmetrical bell shaped. And now what we're going to do is call this the normal distribution. But this is the shape to expect. And again, regardless of whether you're doing stuff that's either about proportions or about means, or whether you're doing things about, one group or two groups, this is what to expect. This is the shape that you're going to end up with. And nothing's going to change in terms of like what we're trying to do. We're still trying to reject the null hypothesis. And in order to do that, we're hoping we still get small p-values that hopefully indicate that our observed result was not a fluke. So for getting our notes started, we're going to be introducing the normal distribution, which again is the distribution to expect anytime that you are doing a randomization distribution and your sample size is a large sample size. By normal, what we're talking about there is that the shape, that the expected shape of the distribution is going to be smooth, symmetrical, bell shaped. They're going to call it a theoretical, like in theory, that's what we're expecting this shape to be. When I say that it's still all about an argument for an HO and an HA, HO is going to still be at the center of it. And the other adjective that they're going to include in here is the normal, the standard normal. You can see my little arrows there that I already put there. Again, what we're hoping for is that if we're trying to reject the null hypothesis, it is that we're hoping that a sample is something that is a contradiction to it, way out on the tails. Now, here's the main key things that I want you to know about what we're doing with the standard normal distribution. First of all, when we say that it's standard, we've used these before. Z-scores. That is something from earlier in the class, which was a nice way of taking maybe two things that have been measured very differently, like SAT, ACT test. They don't measure those the exact same way. But if you wanted to compare them, you could put them in Z-scores as a common way of comparing things that were measured very differently. Same thing here. You might be doing a hypothesis test about averages, one group, two groups. You might be doing things about proportions, and the numbers, because the contexts are so different, the results and the values be all over the place. But with the standard normal, you can shift everything or convert everything back to Z-scores and find a way to see whether something is extreme or not extreme. The reason why zero is being mentioned is because the null value is going to be sitting at the center as what it is that we're trying to reject, and it's going to receive a Z-score, but zero. That way, remember when we did Z-scores, this was many chapters ago, zero was like an average, and anything that was two deviations to the left, more than two deviations to the left, or more than two deviations to the right was like an extreme value. Well, all that stuff is coming back. Now, our statistic which is our whatever we usually get from the whatever value we get from the sample, it's going to get converted. And instead of calling it a statistic, they're going to call it a Z test statistic. And in order for it to be a contradiction to the null hypothesis, we're going to want it to be, either way over here or way over here, like as far away from the null as possible. And the word that we used back then was the word extreme. Right? Anything more than 2 deviations from the center is extreme. And anytime that we do get something that's extreme, like way out on the tails, the p-value for it should be really, really small. In chapter 4, we were counting the dots, and the less dots there were, the smaller the proportion, or the smaller the p-value. And that was usually an indication of, oh, that's really good, because that means that thing that we just observed was probably not a fluke. This normal distribution, which we're about to see here in a few seconds, doesn't do counting dots. It's trying to mimic the same idea, but instead of doing dots, it does area. But to make this sort of like parallel that, the less dots, like the less red dots we counted, or the smaller the area, you're going to expect a smaller p-value. Now, example 1 here really isn't anything about a study. It's mainly just for us to get a real quick feel for how to use the normal distribution. And I'm going to just draw over here 2 of these. They're going to look like this. Just a smooth, bell-shaped distribution, no dots. And it's going to have tail on the left, tail on the right. And to make this feel like a lot like what we've already been doing, when you look at your HA, the alternative, usually it will give us the indication of whether we're doing like left tail or whether we're doing right tail. And then we would go to the left tail, we count our dots to get our p-value. Well, we're going to do the same thing here, except there's not going to be no dots to count. They're going to give us this, right? Or we're going to calculate this, and we're going to have a z-score, and we're going to take that and put it over to the left to get the p-value. So watch, let's do it. Here's where you're going to go. We're going to go to StatKey. And at the home page of StatKey, if you look more towards the bottom, you'll see where it says theoretical distributions, and there's the normal. So go and click on that normal, and you'll see this, just this bald, symmetrical distribution. And it doesn't require you to have to bootstrap anything. It is trying to mimic that whole idea of like bootstrapping and getting your distribution with your hump. But all we're going to do here is just click on the left tail. And look, it's a lot like chapter 4, where we have the default p-value show up. But we know that's usually not our p-value. We usually know that we have to click down at the bottom left to put in our statistic. But today, it's going to be a Z statistic. And right now, there's a negative 1.96. But I want you to go and click on that and change it to what example 1 wants us to do, which is a negative 1.3. Negative. And once you've got it in there, you're going to click OK. And again, it's trying to mimic the whole idea of like counting the dots. And then right above is 0.097. That's what we would call our p-value for some result that had a z-score of negative 1.3. 0.097. And if you're thinking like, what are we going to be using these for? The same way that we would use it in chapter 4, whenever we did a hypothesis test, this would be a way for us to measure whether something was a fluke or not. This p-value, though being large, would not be a significant result. But what I want to do with this little graph that's over here is I want to just do a little idea of shading, like how much stuff we saw. And if anything, I want to just say that it was kind of a lot of red stuff to shade. Watch, I'm going to go back to it. Yeah, like a big chunk of red, which means it was something that was not very far out onto the tail. Still a little bit too close to the center. I might even shade mine a little bit more. Something like that. So again, it's the normal distribution is just a new way for us to get p-values where we can take all these different kinds of studies that are about portions, means, one group, two groups, and just use this one guy to get p-values for all of those. Let's try this one now, where you can reset the graph, reset the plot, like wipe off the whole distribution and do right tail and do 2.2. And notice that 2.2, if we're, I just went ahead and resetted mine, just wiped it all clean. And if I do right tail, again, you don't have to do the 1000 dots because that's kind of already happened. And then the default p-value of 0.025 is there. But where mine says 196, go ahead and click on that and change it to 2.2. So the idea here is that you might have done a sample and whatever the value was for it, you convert it to a z-score, and 2.2 would be considered extreme. And so now you got a p-value floating right above it, a 0.014. Yeah, it's just another way to be able to get p-values. But now instead of having to worry about whether it was a proportion or whether it was a mean or one group, two groups, you just come in here and you do your tail. This one here is the idea that there's not as much red to shade. Just going to show it again. Yeah, not as much red to shade, and that's just to suggest that it was something that was a lot further out on the tail. Which anything out on the tails are good contradictions to the null that are usually sitting out in the middle and give you the ability to reject it. Okay, but that's how you use the normal distribution. Left tail, right tail, put your z value down at the bottom. Again, we're going to be using this as part of hypothesis tests. A quick little recall though, right? We do need to remember how to calculate z-scores. And so this is just a reminder of that. Now, when we used to do this earlier in chapter test one stuff, we would take the mean, we would take the data value minus the mean divided by the standard error. Still three numbers that need to be used, but it's going to be the statistic minus the null value, which is, again, the null value is going to be whatever value you get from the HO divided by the standard error. All right, let's try this. Now, all I'm doing on this page, before we actually get into some hypothesis tests that are part of actual studies, is just a quick comparison of this is the way that we used to do p-values, which is by doing the re-randomizing of like 1,000 dots, and we'll get p-values. And then what I'm going to do right here is suggest that we can now use the normal distribution as an alternative way to get the p-values. Will they be exactly the same? No, but they'll be pretty close, and we'll still be able to use either one of them to reject, not reject. But just a comparison, the old way versus the new way. Now, for this study, you can see here that somebody was arguing that the proportion for some population parameter might be 0.5. And then somebody comes along and says that no, it's greater than 0.5. So this right here would be an indication that we're doing right tail because of greater than. And then this right here would be the null value, right? The value from the null hypothesis. And then we need a sample. They need a sample to see which of those two arguments is more likely to be plausible or to be true. And that's where this comes in. Suppose they did a sample and the proportion from that sample was at 520 agreed out of 1,000, which would be 52% or 0.52. Now, what's really important as you're doing these examples in today's lectures, just like they were, is important whenever we were doing stuff in chapter 3, is like who's who. The null value is the 0.5 because it's from the null hypothesis. The statistic is the 0.52 because it's from what came from the sample. So like everybody's got a little name. You want to think about it that way. Now, if we were to get the p-value the way we did it in chapter 4, like starting in 4.2, then what we would do is go to the randomization distribution. Let's do it. For a second, let's just pretend like we're still living in the world of chapter 4, which would be using these. And if we were focusing on a study that was doing a single proportion, we'd go there. And then we would go to the edit data. And we did some of this in 4.5 where you would put in what actually like was observed. That 520 out of 1,000 said that they agreed. So there's your statistic, the 0.52. And if we wanted a p-value for that, you would do the usual routine, like bootstrap 1,000. You would click whatever tail that you need. Since we're doing greater than, we would do right tail. And you would be like, nope, that's not my p-value. 0.025 is the default p-value. And then down below, where you see my 0.53, we need to update that to be 0.52. And remember, if for some reason Stacky just so happen to already have 0.52 down there, you still need to go and click on that and manually put it in yourself. That way it can update its count and give you the actual p-value, which here we go. I'm going to do 0.52. Click OK. Yeah, my p-value was not 0.25. It's actually 0.099. And you should have something similar, like 0.098 or 0. You might even have one that's like 0.1 something. Right? Like in short, like a really big p-value. Not super huge, but something bigger than 0.05. I'm going to mark that down as 0.099. Now, the last time that I did this, I got like 0.93, but you might have something like 0.97. I remember one time I did this and I got 0.110. So you'll have something like this. Now, to show you that the new way of doing p-values works just as well. Like we should get a p-value that's pretty close to like 0.093. But we need to convert it. We need to convert it to a z-score. And when I say we need to convert it, we need to turn our statistic from a statistic into a z-statistic. And the way we do that is by using this little formula sort of as our guide. So we're going to have z is equal to the statistic, which is the 0.52, minus the null value, which is the 0.5, divided by the standard error, which they gave us the standard error right here, 0.016. And you can put the whole thing into your calculator. You should get 1.25, or if there's anybody who prefers, again, this is optional. If you want to like do the subtraction first and then the division, you get 1.25. But that's the z statistic. So this one right here was called the statistic. This one here is called the z statistic. It's just it being converted into a z-score. And so again, keep in mind the p-value that we got using the randomization distribution was 0.099. We should get something kind of like that. But now, like again, this is chapter 4. By chapter 4, hello, we're going to go to the normal distribution. Hello, chapter 5. And then you don't need to do anything. You don't need to bootstrap here. It's already got the shape of what kind of looks like what you would get if you bootstrap. You would click your right tail. And then down at the bottom, you wouldn't put the 0.52. You would put the z-score for the 0.52, which is right here where it says 196. You need to switch that to 1.25. I'm going to do that right here. 1.25. Click OK. And that would be the p-value right above it, 0.106. Again, not exactly the same thing that I got a moment ago from the randomization distribution. I got 0.099. So I'm going to go ahead and bring this in here. But what I like about this is in chapter 4, there was a few times where I had to remind us all that we would not get the exact same p-values because of the randomizing of it. But now what's pretty cool is that we should now, using this new way of standardizing, get always the exact same p-value. And I'm just going to put little circles around both of these, mainly because I want to just say that although they're not the same p-value, they are both would lead to the same conclusion, and that both of them are bigger than 5%. So neither of them would be considered significant. The result would not be considered significant, regardless of which of these p-values you used. So just all I was doing on this page is doing a comparison of the old way we got p-values versus the new ways. The other big thing that I just want to kind of close out before we get into some examples is that first p-value was based on counting the proportion of dots that are as extreme or more extreme than the observed. And the second one is doing more of a so like mimicking that, like how far out on the tail are you? The more out on the tail you are, the more extreme you are, the smaller the p-value. All right. Well, I'm excited to get into some examples, right? And there's example 3 about to pop up there. I did also think that it might be a good idea to just do a quick this top half of the page is all it really is a kind of just some like golden notes to remind us that the um the z the z calculation is always going to be this statistic minus the null value, which the null value is always going to be at the HO, divided by the standard error. And if you're wondering, wait, where did the standard error come from? They just gave it to us. But we will, right? We have talked about standard errors before. We used to get those because we would do the bootstrapping ever since like chapter 3.3. There is also a formula coming up down the road. We'll be there before you know it. There's a formula that we can use to get standard errors. But mainly what I have here is for your statistic. It could be any of those 4 different things: single proportion, single mean, or the X bar for 2 groups, the p hats for 2 groups. All of those are considered what could be the statistic in the first position of that formula, minus the null value. And I've been kind of trying to hold off on this. Sometimes when we say the null value is going to have a number, like we're going to be able to see the number, but that's whenever it's just one group. But then sometimes the null value, we don't see it immediately. These are the ones that we've seen before, like in 4.5, whenever they're saying that the both groups are the same or have no difference. Maybe I'll go and sneak those in there. Whenever they're saying the groups have the same parameter, same value, or that there's no difference between the 2 groups, you don't see the null value, but you got to keep in mind that it's a null value of 0. Okay, it's saying that there's zero difference between the two groups. And the formula for standard error is coming soon. Okay, so let's try this. Example 3 is divorce morally acceptable in a study conducted by the Pew Foundation. Here's what they found out: 67% of women in a random sample viewed divorce is morally acceptable. But then there's the word test. We want to test. Now, I'll let you finish, keep reading that sentence test to set up the HO and the HA. All right, just take a few seconds to do that. Okay, so again, as you're working through that, just keep in mind what part B is. B is actually wanting to know, what did the sample say? So you'll see words like statistic. Yeah, give the value and the notation for the sample statistic. When they actually did survey people, what did they find out? So again, the big deal between this is just being able to see all this information and put where the information needs to go. All right, but here it comes. They wanted to test whether this provides evidence that more than 60% of women view divorce as morally acceptable. So that one sentence that talked about test, that is where we get that this is going to be about a proportion. Again, because we see percentages. Maybe it's 60%, or maybe the proportion is more than 60%. Now we can see it, right? The sample's there. Whenever they did the actual study and they did a random sample, they found out that 67% said that they reviewed, they thought divorce was morally acceptable, specifically for women. Now, what we're going to do next is, again, introduce the new way to get p-values, which is with the normal distribution. Now, what I'm going to do is just real quick under here put 0.60, and this is 0.67, just so that when we do the actual calculation for the z-score, which is at the very top of the page, it's the statistic minus the null value over the SE. And you'll see why. Wait, why did we have to put them in percentage as purely decimals? Is look at the last sentence of that prompt. That's where they introduced the standard error, but it's not a percentage. It's purely a decimal of 0.021. So that's why instead of doing the keeping it at 60% and 67%, I switched those to decimals. So our statistic is 0.67 minus our null value is the 0.60, and our standard error is given to be 0.021. And again, you could just put this directly into your calculator. I mean, your calculator for some of us might need us to put parentheses around here, and you should get 3.33. There are some of us who maybe would prefer doing the subtraction first, hitting enter, doing subtract, hit enter, 0.07, and then doing the division. Again, we'd still get 3.33. And for my z-scores, if they don't already stop at one decimal or two decimals, they go on and on and on and on. I say round to just 3. That should be good enough. But this is optional. You don't have to do that. If your calculator is happy with just putting it in with the numerator, with the parentheses divided by the denominator. But for some, I do notice sometimes students when I'm teaching and they come talk to me, they're like, I'm not getting the same answer. It could be that your calculator needs the parentheses for the numerator. All right, but we've got the 3.33. And notice that is something that back in unit 1, we would say, hey, that's extreme. right? And we're still going to loosely use that. It doesn't exactly perfectly work out to be two, anything more than two being extreme. We can loosely use that. But three would be considered something extreme. That would be more than two deviations above average, extreme, way on the tail, expecting a small p-value here. But let's do it. Let's go to the normal distribution. Keep in mind what tail that we're going to be using. It's greater than. Now, all we need to do is just wipe the graph clean. And since we're doing HA P greater than 0.60, we need the right tail. And then down at the bottom right, again, don't believe that the p-value is 0.025 just because it's the first thing that pops up. Click on the bottom where you see mine saying 1.96 and change that to 3.33. And once you hit OK, that's your p-value floating right above it. And because we see something like 0.00043, that's a really small p-value. Like 0.0, that was just one decimal, would be small. 0.0 would be even smaller. 0.000 is like really small. Zero point zero 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 0.00043. Now, previous to this, we've been using a lot of 5%, but I want to go ahead and bring in 1%, which is the lowest that we're ever going to go, like the smallest that in this class we're ever going to see whether our p-value is smaller than that. So I'm going to box this up as being the answer for D, but then right next to it, I'm going to put alpha of 1%. And usually we would say, is this smaller than 5%? But this is actually 0.004 is smaller than 0.01 as your alpha. Now, anytime that this happens, this is a victory for HA, that there is evidence that what was observed was not a fluke. And so you might just take a quick little peek back at the page 3 of your 4.3 notes. We said anytime the p-value is smaller than alpha, that's when we can reject the null hypothesis and start to say that there is enough evidence. But this is optional. But anytime that you get a really small p-value like this, the smaller the p-value, the more likely that it was not a fluke, which would be stronger evidence. So I'm going to go ahead and start doing this sometimes, where we're not going to just say that there is enough evidence. We can say that there is strong evidence. And usually we'll say strong evidence anytime that we notice that a p-value is not just 5% less likely to have been a fluke, but a less than 1% chance that it was a fluke. So again, the smaller the p-value, the stronger the evidence, because the stronger that we would consider that it was not a fluke. And now we're just going to go ahead and put back here, what the whole study was about, whether the proportion of women who say that divorce is morally acceptable is greater or more than 60%. So there is strong evidence to suggest that more than 60% of women view divorce as morally acceptable. Now, if on the homework you stick to the usual, there is enough evidence, that is totally fine. But if you do happen to get into the habit of noticing, ooh, that's a really small p-value, you can change it up and say strong. Yeah. So if anything less than 5%, there's enough evidence. anything that's smaller than 1% chance of being a fluke, you can say strong. Alrighty. Let's try another one here. Now, for a lot of articles, they'll tell you whether they're using 5%, 1%. If they don't tell you, or if in the homework that you're doing one of these problems, or even a test that you end up doing later on this class, I think for most of like the test problems, I start off with always telling you, do 1% or do 5%. But if ever I don't, or like even like on a quiz or like in a test, if it doesn't say it, then go ahead and assume that we're doing a 5%. Right. And I think that's what happens on this one. I think it doesn't tell you to do 5% or not. So just assume 5%. All right. But I want you to go and read this prompt. And I want you to maybe, again, if you're still trying to get into the swing of things, start off with the sentence that says test. So you can write your HO, write your HA, decide whether we're going to be using M's or P's, about whether it's one group, two groups. HO always uses the equal. And then for B, all they want you to do is that. Subtract the proportions. And I would do these as decimals. Because I think, yeah. Let me be quiet for just a little bit, or pause the video, do part A and B. All right, here it comes. So they wanted to test whether there's a difference. So already that's going to be the not equal to between the proportion of men and women who say divorce is morally acceptable. So proportion of men, proportion of women, proportion of men, proportion of women. Now the null is saying that the two groups are the same, which not necessary to have this as part of your answer with your homework, but this would be null value of 0. You're going to see why that's important in just a second. And also another thing is just make a little note that this is a two-tailed test, which means we're going to need to do a special something whenever we do our p-value. What was actually observed, if we're doing proportion of men from the sample minus the proportion of women, was men was 67%, female was 71%. But let's do the men first. And again, I recommend that even though they gave it to us as a percentage, go ahead and just start switching these. Like, don't even write them down as percentages. Just go ahead and write them down immediately as decimals. Because a lot of times, look at this, the standard error was given as just purely a decimal. That way, we're working with decimals at the same time that the standard error is purely just a decimal. Again, once we've done the subtraction and we get 0.04, that's our statistic. Then as they ask us to calculate the Z statistic, again, it's the same routine. Your stat minus the null over the SE. Yeah, I want you to go ahead and just pause the video and go ahead and do that. Do your statistic minus the null value divided by the SE. Now, if it doesn't ever say, to round to how many decimal places, usually I do 2. So that's our statistic. And the null value, which is saying that there's no difference between the two groups, you'll just have to have this written somewhere like on your reference sheet. And anytime you're saying that the two groups are the same, either the same proportion or same average. That's null value 0. And then the standard error was just given to us. Again, we'll introduce a formula for that when we get into chapter 6. You're going to get 0.04 divided by 0.29, which gives us 1.38. Now, this is what we're going to take over to the normal distribution to get a p-value for. So again, the way that I have set up the lecture is the same way it's going to be in the homework, where it like guides you from the next thing to the next thing. So once you have the z-score, that's the next thing to take you on to getting the p-value. Now, keep in mind that when we go to get the normal distribution, make sure that you're attaching your stat key with your homework to get credit for this. You don't want to lose any points just because you forgot to attach your stat key. But I'm going to erase the plot. It's a two-tail, so let's just go ahead and just do that. It's a two-tail test. But now the 1.38 only makes sense to put on one side or the other. You got 0 in the middle, you got negative on the other side, you got positive on the other side. We're going to go with the positive side. So down there in the bottom right, where you see 1.96, click on that and change to 1.38. That was the Z statistic. One 0.38. Click OK. And you get 0.084. And that would be our p-value if we were only doing a right tail test. But because we're doing a two tail test, you need to add up the left side, the right side, or what we did when we first introduced p-values in 4.2 was we said you could just do times 2. So yeah, let's go and do that. We're just going to do the times 2 one. Yeah, so the p-value is not done. We're going to take the 0.84. We got to double it. And we'll get 0.168 for the p-value. Now, once you have your p-value, you move on to making your conclusions. And remember, the generic formal conclusion is like multiple choice. Reject HO, do not reject HO. The only times that we can reject it if it's significant, meaning the p-value has to be small. But if they did not say what alpha to use, then go ahead and assume that we're going to use a 5% alpha. And that p-value is really big. There's more than 5% chance it was a fluke, like a 16.8% chance it was a fluke. So no, that is not a significant result. So we do not reject the null hypothesis. Furthermore, we would also say there is not, or again, the homework answer key is going to say do not reject HO. You could put fail to reject HO. This is not a victory for team HA. And we would say there is not enough evidence to support the alternative. But don't say just that there's not enough evidence to support HA. What was HA about? It was whether there's a difference in the proportion between men and women who say that divorce is morally acceptable. And you're totally also okay just to reuse like their wording up here. Right. They were trying to see whether there is a difference in the proportion between men and women who say divorce is morally acceptable. There's just not enough evidence to back that up. All right, so let's go ahead and put that in. There's not enough evidence to support that there is a difference in proportion between men and women who say divorce is morally acceptable. So although when they did collect the observed men and women, it did show that men was higher by about 4%. Again, there's that 0.04 up there. There's a big time chance that that could have just been a fluke. And that if they were to do maybe another repeat of the study with a fresh batch of men and fresh batch of women, it could very easily like flip around where maybe women is higher or come back out to where they just stalemate at being the same thing. All right, last thing for this section, which is actually more so just an extra example for you. I want you to pause me and I want you to try this one completely on your own. And all I'm really going to do here is just a little template where you need to read the statement to see what's being tested. You need to see what's the value for the statistic. It's going to give you a number. And then when you're ready, you're going to take the statistic, whatever you get in part B, minus the null value. So whatever's up here for the null, whatever's right here for the statistic, you're going to divide by the standard error, which you'll see it's given. Um, I would, whenever you get done with part C, just do 2 decimal places. And then that is what you're going to take and put into the normal distribution, whether it's left tail, right tail, two tail, you'll see in a second. And then just use a 5%. And again, if your p value is smaller than that, bigger than that, that'll lead you to be able to reject the HO or not reject the HO. Right, I'm just going to put a little blank here. This is the one where you say either reject HO or do not reject HO. And then right here is where you say your conclusion and context there, you know, is or is not enough. I'll let you fill it out for the alternative. All right, so go ahead and pause the video. And again, try this whole thing, right? See if you can get through the whole entire thing. And then I'll go ahead and unveil the answers. All right, so assuming you gave this thing a shot, here it comes. They wanted to do a test to see whether whether there's enough evidence that the mean length of a baseball game is more than 170 minutes. So whether the mean is more than 170 minutes. And boom, that's all that we need for A. For what was actually observed from a sample, which would be the sample mean, X bar was 179.83. And they say that right up here, whenever they did a sample, they got a mean of 179.83. And this is all we really need to write for the homework, but I'm going to write a couple other things. This is the null value. This right here, of course, they already say it. That's the statistic. This is also a right tail test, extra little goodies that might help us out. And so when you do your statistic, when your Z statistic, it's going to be the 179.83 minus the 170 for the null over the standard error that was given way up there, which is 3.75 that they just gave to you. And then whenever you calculate this, you should get 2.62. 2.62. And again, your calculator might require you to put parentheses in there. And if you want to subtract that first and get 9.83, then divide. But then you would take the 2.62 and you should have gotten a p-value of 0.0044. But if you didn't, here's how we get it. We would go to, or maybe you did. You just want a real quick confirmation that yeah, you did it the way we should have. You would just erase the plot. If you were working on another example, you would click your right tail, and then right here at the very bottom, you would put the z statistic of 2.62, and that's where the 0.0044 comes. Now, again, in order to be able to reject the null hypothesis, it needs to be, I'm just going to put it over here. It needs to be that this is smaller than your alpha, and it is. Yeah, 0.0044 is smaller than alpha, so there's a less than 5% chance that this was a fluke. So we can reject the null. There is enough. Now, because that is smaller than 1%, you could say that there's strong evidence. But since we're only basing it off of a 5%, I think a lot of us might just get into the habit of doing, there's enough evidence. But if anyone caught on to that, hey, that also would have been smaller than 1%, then you could have done that they're strong. And then again, this is called the conclusion in context. So we want to make sure that we mention what the study was about. And it was about whether the mean length of time, and I'm going to go ahead and interject the word all, right? This was not just about wanting to say something about the sample, but this is trying to say something about all baseball games. And I know that this is probably like a dated sort of example because they have, since this example, changed like the rules, some of the rules to baseball to make the game move a lot in a faster pace. But at the time of this study, yeah, there's evidence that baseball games do tend to last more than 170 minutes, right? So maybe up to like 3 hours. But all right, but I hope that went well again, and I'm also hoping that as we've now, that's the only section that we have for chapter 5.1. That's it. I hope it should be a pretty smooth homework. Again, refer to the lecture, refer to the video recording for how to use the normal distribution. But then we'll do more hypothesis tests in chapter 6 to just help us really get those nailed down. But I'm gonna go to end the recording and reach out if questions show up.